In this video, I'd like to help you get some exposure to the nature of the chi-square distribution. And before I do so, I'm going to present to you the distribution that you probably have some familiarity with already, the Z distribution. So you recall that the Z distribution has a mean of 0 and a standard deviation of 1, and it is often referred to as having a bell-shaped curve. So we have positive values and negative values. Most people score in the middle. Now I say people, but it could be cases of any nature. Now the chi-square distribution, it looks very, very different to the Z distribution because it actually only has one side to it in the sense that it's extremely positively skewed. There are no values less than 0, and there are no values less than 0 because all the values in a chi-square sense are squared. And when you square values, you only get positive values. So any possibility of negative values have all been pushed over to one side of the distribution. And this is what a chi-square distribution looks like with real data. I think I have 100,000 cases here that I generated this distribution with. And this is the distribution to which we compare obtained or calculated chi-square statistics, or statistics that approximate the chi-square distribution. So the Pearson chi-square analysis, for example, is known to produce values that follow approximately the chi-square distribution. And that's why it's known as a Pearson chi-square analysis. For example, when I tested the difference between the proportions associated with my ex-girlfriend's success rate of correctly identifying Pepsi and Coke. This is also true in the textbook where I talk about the percentage of individuals who are diagnosed with dyslexia who are left-handed versus right-handed. That analysis, which is testing the differences of the proportions, the ultimate result you get from applying the formula is a value that follows the chi-square distribution under the expectation that the null hypothesis is true, which is that there is no difference between them. So it's a representation of random variation in the context of squared values. It's not the case that all squared values will follow the chi-square distribution, but the Pearson chi-square statistic does follow it very closely. And here are some attributes associated with the chi-square distribution. It has a mean of 1.0. So that makes it different to the Z distribution, which has a mean of 0. It has a standard deviation of 1.43, which is different than the standard deviation of 1 that you find in the Z distribution. It's a skewed distribution, highly skewed, 2.87 skew. It's highly kurtotic, 12.60. I have a maximum value of 21.45, so there is actually a chi-square value that is as large as 21.45, and that happened strictly by chance. So there's nothing going on in the population. You can get a chi-square value as large as 21.45, but it's extremely rare to get it. Very, very rare. So if you were to observe a Pearson chi-square value that was as large as 20, you would reject the null hypothesis because it's such an unlikely event to occur strictly by chance. Now, the demarcation criterion that we use in statistics is 95% confidence, usually. And the 95th percentile in this chi-square distribution that I generated with a computer program, that corresponds to a chi-square value of 3.87. And I mentioned in the textbook that when the chi-square analysis only has 1 degree of freedom, and I should say that this chi-square distribution that I created is with 1 degree of freedom. The chi-square distribution with 2, 3, 4, and 5 degrees of freedom is different to what this looks like. I may create a video to show you what that looks like at some point, but with 1 degree of freedom, which is a very commonly applied analysis, like the Pearson chi-square analysis that I used to test my ex-girlfriend's success rate was with 1 degree of freedom, and the left-hander, right-hander dyslexia analysis was also 1 degree of freedom. So they follow this 1 degree of freedom theoretical chi-square distribution. So going back to the 95 percentile, a chi-square value of 3.87, which is somewhere about here in the theoretical chi-square distribution, corresponds to 95th percentile. So only 5% of chi-square values can be expected to be equal to 3.87 or larger when the null hypothesis is true. Now, I could end this presentation right here and you'd be taking away some really important knowledge about statistics in the context of inferential statistics, any type of inferential statistic. is fundamentally based on calculating a statistical value and then comparing it against a distribution to determine how likely such an event could have possibly occurred when we expect the null hypothesis to be true. I could end it right here. It'd be great. I want to go a little bit further, and I should say that if you don't like learning a little bit of an extra connection between concepts and operations in statistics or any other discipline, do not move forward, because you might feel like you're getting confused rather than gaining knowledge. So stop here if you don't want to carry on. So for those of you who do carry on, I'm going to show you something that's very interesting about the chi-square distribution, the theoretical chi-square distribution with 1 degree of freedom. So 3.87, if I actually square root that value, I get a value of 1.967. Now I rounded this to 2 decimal places, but let's just look at this 1.96 value. Forget the 7, because that shouldn't be quite a 7. It should be a bit lower than that. And it's not, because I rounded the 3.87. Do you remember a value of 1.96 anywhere along the lines of you learning statistics? Think about it. You have. 1.96 corresponds to the 95th percentile in the Z distribution. And I should say negative 1.96 all the way up to positive 1.96 incorporates approximately 95% of the entire observations in the Z distribution. So because this square rooting of a chi-square of 3.87, which corresponds to a 95th percentile, corresponds to the Z distribution, what would happen if I square rooted all of the values associated with the chi-square distribution with 1 degree of freedom? Well, I did just that. And then I created a histogram out of all those square rooted values. This is what you get. You get a distribution that still has only positive values. It was impossible to get the negative values out of the chi-square distribution. But what's happened is that the distribution is now taking on characteristics that look very, very normal to me, like a normal distribution. And what's more is that the 95th percentile in this square-rooted chi-square distribution, or what I call here the inverse chi-square distribution, kind of as a joke, that I created a new distribution called the inverse chi-square distribution, well, that's really the Z distribution. So the chi-square distribution with 1 degree of freedom and the Z distribution are actually the same distribution. And again, the 1.96 value, which is about here in the distribution, corresponds to the 95th percentile. And that's not a coincidence. There's a fundamental connection between the standard normal distribution and the chi-square distribution with 1 degree of freedom. But this connection breaks down once you get into chi-square distributions with more than 1 degree of freedom. And that's why it was invented. You might be thinking, why would we bother inventing a new distribution when the Z distribution exists? It's because the chi-square distribution can be expanded to having 2, 3, 4, 5, 6 degrees of freedom, whereas the Z distribution cannot.